Okay. Thank you all for attending today. Welcome to the latest installment of the Audio Engineering Society Standards Committee webinar series. I'm Richard Cabot, the Standards Manager, AES Standards Manager. These webinars are held every other month and showcase technology from current work in one of the AES standards working groups. For this webinar, we're pleased to present Anthony Kazub from the Canadian Broadcasting Corporation, who will present on the AES72 standard, which covers the transmission of AES3 or balanced analog signals over quad twisted pair cabling. Anthony's the chair of AES0505, which is the working group that handles analog interconnections. Anthony?
Thank you, Richard. We're going to talk a little bit about a thing called quad twisted pair, which is AES72, and it's for everyone. As my colleague Jeff Berryman said, you know, I'm a bit of a twisted pair myself. I started a website called rj45.audio, and I've kept a website called quadtwistedpair.com, where I'm a fan of the technology, you know, a real fan of what is out there. You know, I'm a historian. You know, I curate a couple websites. I'm a machinist. I'm a metrologist, and I'm a media maker. So I present often. Oh, sorry, I didn't mean to click the link. Don't click the link. Oh, Anthony, why did you do that? Websites and presentations, they're so interactive these days. So I will get. I'll get these slides posted. I think we'll be able to do a Q&A after the fact. Oh man, I have 100 slides and it's crashing slowly. So let me go back. I was involved. You know, my background is I was a recording engineer. I started in the recording industry. Recording studios. I built big systems. I built patch bays. I built mixing consoles. Rebuilt, hot rodded, recapped, rebuilt. Had fun with some of the very classic pieces of audio equipment that are available in the industry. Worked with some great names, you know, had some great experiences across Canada with various studios, various methodologies of how people actually built things. Myself, I was a huge fan growing up of Wardbeck Systems mixing consoles, and so as I grew up, I started building them and hot rodding them and hot rodding Studer tape recorders and building things. As I grew up and learned a little bit more, I got in as a field applications engineer with Wardbeck, whom I admired. Worked with them to develop some of this system that we're going to talk about today, and worked with them on some IP audio solutions as well. So now I'm with the Canadian Broadcasting Corporation. I'm a senior systems designer, and I deal with like Richard says, some big systems out there. Everything is tied together. Everything is, patched in together. Everything is virtualized. One thing to another. It's all interconnected. So I got involved. Once I left Wardbeck and got in with the CBC, got more involved with the Toronto Engineering Society, Audio Engineering Society, and the grounding practices and ENC practices, tying all of these things together for audio connectors. So in 2014, 2019, we got together as a group, the subcommittee, and we had come up with a standard for interconnection of application of RJ40 type connectors for twisted pair cable of audio connections. So we looked at, the commonalities. We did a field survey of some of the things that are out there: channel link, signal polarity, phantom power compatibility. What types of things are in the market, and the practical applications of some of these details. And I'm talking about, like, I bet we got 38 people on this call. I bet you if you walk within 5 meters of your current situation, you may find yourself with one of these RJ45 cables that is, it's got some really cool properties that we're going to talk about for moving analog audio and AES3 audio. And it's very simple. You look at what the XLRs used to be, both male and female, and there's a positive and there's a non-inverting, right? And then there's a ground. And with something like this, which is the RJ45 DB25 type of connector, or sorry, RJ45 AP8C type of connector, you can map 4 channels one to one. So we need your help. Again, we have 40 attendees now. We're up to 40 here. And for those that remember 1990, well, I was in grade 1. To put it into perspective, that's so 1990 they decided between pin 2 and pin 3 should be high, and they came up with pin 2 ultimately. And I don't think it was a result of this spinner. It was through a series of discussions that people like the Richard and Bill and all the people in those standards committees worked together, and really we're suffering the same kind of problem statement, which is there's no consistency between the link assignment between the manufacturers for RJ45 audio. And who benefits from this? Manufacturers, users, production, post-production, broadcasters. The AES spans a full range of users that benefit from these types of recommendations. I'm sorry about the slides. I'll get the slides posted to, and I'll move a little slower. I apologize. And it's I'm just reading them anyway, so please just listen to my words. Twisted pair. This isn't a new concept. This is a classic concept invented by this guy who did this telephone thing. I don't know. He made a little bit of money doing it, and he twisted the wires together, and all these magical properties came from that, and that was the first form of programming, right? That was the first form of moving signal from this place to this place, was literally patching those twisted pairs. So a building would have these multi-pair cables that come in, and you literally patch this signal to this signal and this signal to this signal, and then they would pull out a pair of those wires and they would tie it down to a terminal block, and they would twist them together, and they'd tie it down to another terminal block, and they would make those interconnections that way. And it involved this soldering thing. And people, we want to get away from soldering. Soldering is it's toxic. We want to get away from that. So what happened in the telephone industry trickled its way into the broadcast industry, and the broadcast industry started adopting some of those practices, and some of those practices started getting mapped on top of things, and then bad practices develop when you have multiple adapters plugged into adapters, plugged into adapters, plugged into adapters. And then, somebody like me comes along and says, I read Neil Muncie's page and, Bill's work, and say, well, cable shields may not be required at all in the applications where nearby electric and magnetic field energy is reasonably low. And a lot of these things were designed for all of these transmitters and receivers that were in like really high sensitivity areas, or designed for transmitters, AM transmitters. But you can get away with, just running a twisted pair to a piece of equipment and getting away with it. So a lot of folks did. But there's no standard for which pair is which, and how does it connect from one to the other? What is pair 1? What is pair 2? What is pair 3? What is pair 4? What does it do? If I'm running AES through it, well, is it surround sound? Is it left, right, center? Because, with one of these cables, with a single RJ45 cable, that's 4 AES pairs. So that's 8 channels of audio through a single interconnection. So we're working as a group to talk about that. And when things are balanced, and when things are properly balanced, it's not bend the rules or break the rules, you just play the game of moving twisted pair as you need it from place to place in order to move signal from place to place. Then you run into the folks who deal with the TRS connectors and, solder those TRS connectors into place, and ultimately, start plugging it into other pieces of equipment. And then when you get into that, on this one piece of cable, I have 4 conductors, so I could do a transmit and receive. So imagine if you had the ability to say, well, pair A and pair B are send, and pair 3 are receive and receive. Well, but which end is transmit and which one is receive? So we started, asking all of these questions as a group, because as some of these users started doing these experiments, it ultimately brought up all of these very interesting questions. And then you start integrating the 50/50s, where, part of the twisted pair gets bonded to traditional infrastructure. Here, they're using a standard cable tester, just off the shelf cable tester, to test an entire patch bay. Then you ask yourself, well, can I do it with microphones? Well, how do I do it with the Shield? How do I do it with Phantom Power? How do I do it with all of these different things? What channel is what channel? Who controls that? Well, it might be us. There are companies who are starting to put out these professional products. There are companies who build these breakout boxes. There are companies that build these, breakout snakes that tie them to the color code. There are companies that design. This was one of the products that I did as my thesis for Wardbeck systems. Is there's little AES59 connectors to what is now AES72 4E. So breakout snakes, ganging between, boxes, going in one box and out the other box, putting these things in parallel with one another, going in one box, coming out the other box, right? So you have breakout snakes, you have RJ45, and then breakout snakes. So I'll talk about this. And then you have, these little widgets all the time that are starting to show up. Here's a Pro Tools system hooked up, where one piece is effectively right on top of the other one, and a simple 1 foot little patch cable, or 6-inch patch cable that's shielded, connects one device to another device through AES59 connections, just a click away. Here's a company that is starting to gravitate towards it, a Studio Hub. They just put out this AES59 to AES72 Type 4E adapter. So now people are starting to see that there is this huge potential of using all 4 channels simultaneously. Large companies, like Whirlwind, are starting to do these in and out and parallelism boxes and these throughputs. There's also there's a ruggedness and a trusted to some of how these manufacturers build these devices and put them out into the industry. What used to be a luxury item that's just like a 4-channel drop box on a stage is now just a couple folded pieces of sheet metal, and that's about it. But across those 4 channels and across those 8 pins, what we observed as a group was incompatibility between all of those different pinouts, between all of those, how manufacturers started, blurring the lines between what they used, and I'll talk about, some of those hangovers. And I say, but why? Why does it become such a confusing thing? How does it ultimately work? It was a random thing. People started adopting this concept and hooking channels up to one another, and this is where we found ourselves in as a predicament. In the past, the groups, the working groups, have standardized certain things like AES14, which is the standard XLR connector. AES59 is the standard DB25 connector and the pinout for that. AES14 is a designation of, the TS and the TRS connector, and AES72 is dealing with the RJ45 connector, not the Ethernet connector, but just the RJ45 8P 8C connector, as we like to call it. The AES, for those who are new to the group, we've got 45 people online. Please take a look at the other standards. They're there so you don't have to reinvent the wheel. And what AES48 really taught me is just really how to guard yourself towards the best practices of how to build equipment and how equipment should integrate. Last week or last month or the last presentation, Bill Whitlock, who's on the call now, gave a fantastic presentation about common mode rejection. And I can't do it justice. I have a hard time, even talking to Bill sometimes, because I'm just intimidated by him sometimes. It's for him to comment on this work is just such an honor and a pleasure to have him look over that. And in that working group, we work together to come up with some kind of standard for maintaining that practice and promoting that practice. And all of these standards, they work with one another. It's very important to remember that these standards, they all tie together. So, how an XLR behaves and how a DB25 behaves and how an RJ45 8P8C behaves. These are things that we're attempting these are things that are standardized. How there are contemporary practices for grounding, and there are also termination and practices for cable shields. And these are big, huge topics. And one of the ones that's not so well defined is the topology of what's actually behind those connections. And cable has been out of scope for a very long time for the AES. We haven't dealt with cable, but in this standard, we did have to deal with cable. But in the other group, what we're trying to define is, well, really, what is a balanced analog audio output and what is a balanced analog audio input? And Bill did a fantastic presentation on what the work has been doing in the SDO 505 group. And it's an older project. It's been sitting on the shelf. It's got a 100 designation, so it's a 152. So we've taken up this, and we're trying to define that, the impedance balanced and, the magic that allows QTP and other audio standards to work, effectively day in and day out. But of course, I love saving money. Part of the audio world is saving money. And being hip to the newest, coolest technology is very important to us as industry installers and industry builders. And I'm talking less cable and installation and termination, and how much less? Well, like here, this is a little 1 foot patch cable that's 73 cents terminated at both ends. It's like, whoa, this is very appealing. Okay, I can buy a patch panel. How much is that patch panel? $8. Are you serious? That thing is $8. I can do that on $8. Wow. So I can crimp this. Like I just put it in my crimper and and it chops off the ends. I don't have to do that. I don't have to solder anymore. I don't have to have a respirator when I do work anymore. I don't have to do any of that stuff. Okay. You have my full attention. You mean I don't have to solder DB25 cables anymore? What do you mean? Okay, go on. So this trend, I call it audio over IP. Independent pairs, or individual pairs, as I like to call it. So it's using these 4 pairs as an audio snake, using unshielded twisted pair and shielded twisted pair networking cables, and it's leaving the patch rooms and it's leaving the fields and it's starting to enter the pro audio industry. Why? Well, like I say, it's cheap. It's just abundant. I can just pull it out of the tray. Yeah, sure, no problem. Just run one of those. And this is just everywhere. This is just absolutely everywhere. Like I said, I challenge any of you to run 5 meters and see if you run into one of these things. But you have 8 pins, and like all things, every engineer looks at 8 pins and goes, well, this is how I do it, and this is how I do it. And there would be some idealism that, but you start unraveling the audio onion. So in honor of Neil Muncie, we're gonna go down a little bit of the audio onion rabbit hole. So why does there need to be an AES standard? What's the problem with standards? Nobody reads all of them. The normal joke is there's too many of them, right? The problem with standards is there's just too many of them. My problem with standards is you can't read all of them. Like you just can't. Like it's so, but it's there's people, industry professionals in this audience who are looking to do their research to understand the standards, and this is very, very important, and this is why things need to be standardized, because folks who are in this audience, ultimately profit and benefit from this. And this RJ45 8P8C connector and quad twisted pair, and we'll talk about why we called it quad twisted pair. It's just everywhere. Datacom, just everywhere. Ethernet. It's not Ethernet. Let's not call it Ethernet. Whatever you do, don't call it Ethernet. It's high volume. I can go to the Home Depot and build a recording studio out of stuff that's out of the Home Depot. But because of that, because it's just so ubiquitous, it's just manufacturers have developed their own way of interconnecting these devices from one thing to another. And there's only 4 channels between these devices. So we identified variants, and we asked vendors to identify compatibility, and and this is all in an effort to alleviate problems. We're bringing attention to the problem. And again, like the audio onion's deep, right? So the deeper you go into the problem, the more levels you discover and the more you want to cry. But I love the taste of onion. So we have the pin 1 problem, it's still there. Bad electrical wiring, still there. Ground loops, still there. Plastic XLRs, still there. See Bill's presentation last month. Then we got this new problem that I've coined. It's called the pin 2, 16, 5, 19, 8, 22, 11, 25 problem. And I'll talk a little bit more about that. But what the AES has given us is this ability to talk about how these signals reference one another and interconnect with one another. And when it comes to digital or audio signal circuitry, the AES sets a bit of a specification of like how the shielding enclosure should work and how the cables should tie from one another. So AES72 deals with what the connector is doing, and other groups are starting to deal with what the shielding is doing. But I'm gonna pretend like you don't know anything, but I'm just gonna talk. So there's cat cable. Well, it's different twists per meter on each channel. What does that mean? So every pair that's inside here is twisted at a different twist ratio, and Bill will tell you that's a really good thing. And I'm not even gonna get into that. He could write an essay on that. But every pair is twisted at a different twist ratio, and then they're twisted all around. Oh, it's just incredible. It has 100 ohm impedance, so it's within the AES's 20% AES3 specification. There's 2 types that you will see everywhere. This is a solid core, right? It's just a solid piece of copper, and then you'll see stranded for temporary installations. And what I mean by temporary installations, I mean like patch cables. So, the TIA, the Telephone Industry Association, oh man, again, if you want to solve a problem in audio, look to the telephone industry. They solved it 20 years ago. And they had bonding considerations, and they told us all about, all of this cable. And when you get into these quad twisted pair variants, like there's Cat 3, and this is dead. There's Cat 4, Cat 5, UTP, and then shielded twisted pair. And then you have enhanced Cat 5. And the bandwidth of this cable just goes up and up and up. And then also the twist ratios go up and up and up as the cable gets implemented. So these cables are up. They're meant to operate in the high frequency spectrum, and we're doing baseband with them. We're running DC over them. And what you'll see in the industry is a global abundance of variants. And there's unshielded twisted pair, there's shielded untwisted pair, there's shielded braided. So there's, and this one they called it shielded braided foiled. I don't even know. And then foil shielded, and the braided shield is great for EMF, but you've got electrostatic for the foil. The foil doesn't do anything in terms of magnetic. It's just all electrostatic. And so there's some benefits to all of these different wires, and how you choose to use them, and where you choose to use them, and how you choose to implement them is greatly different. And again, I got to reach out to my AES colleagues and say, this is new territory for the group of us. So there's research to be done, and there's opportunity for people to learn more about what is actually happening inside these pieces of wire. Again, like I said, twisted tightly together, then twisted together throughout the Cat 5, Cat 6, and Cat 5e. So they twist ratios are different per wire, and then they twist all of the wires together as a bundle. And that's like common practice. This is like the best thing you could possibly do for audio cables. And we grouped all of those UTP, STP, shielded twisted pair. We grouped it all, and we just called it quad twisted pair, because there are certain things you can do with or without a shield. And each pair, they're twisted together in order to cancel out electromagnetic interference. That's where your huge benefit of the twists come into play. And then there's also shielded, unshielded, and then there's also using that shield as a return path for phantom power. So there's a lot of different ways that you can get into. Like I said, you look at this very simple, unassuming connector, and this isn't even the one I'm the best of the bunch because this isn't a shielded version, but it's 1, 2, 3, 4, 5, 6, 7, 8. In an ideal world, it would really go, 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, 6, 7, 8, and it would really, in an ideal world, go red, orange, yellow, green, blue, violet, gray, white, black, red, brown, red, orange, yellow, green, violet, and it would repeat. But we didn't luck out. We got this industry that's full of nefarious cables that have solids on pin 1 and on one version, and solids on pin 2, and we've got these standards that we have to adopt. So we set out and we said, okay, look, this is this is pin 1 when you look at it. There's this pin 8 when you look at it, and we had to illustrate it, because if you go into RJ45s and all of these different type of connectors, there's variants that there's a legacy of RJ45, and the Ethernet cable, the Ethernet port that we're kind of hijacking an idea on is really a derivative of RJ11, which is our telephone, and it brings us some interesting problems where if I have these middle 2 pairs, that's where the telephone used to go always, was on the middle 2 pairs. So if you had a 4P, 4C, the middle 2 would always be the telephone. So some TIA standards and these things started using pair 1, and then pair 2, it deviates. And that's just a hangover that all of these standards and documents have created. Is again, reading documents and standard documents is there's 2 competing, versions of this. If you go 5 meters the other direction and you find a second RJ45 cable, it could very well be that it is a TIA-A or is it a TIA-B. Like I said, the middle 2 pairs were reserved for the telephone. And then what they did was they split around the middle 2 pairs, sometimes pair 2, and then they did 3, and then they did 4. And in Ethernet, you'll see that they did transmit on one and receive on the other, and then the other 2 pairs, they just left sit idle. But, like I say, you go 5 meters one way and you might find a TIA-A, and then you go 5 meters the other way and you might find a TIA-B. And what did they do there? Well, they went pair 1 down the middle, pair 2 off to the side, pair 3 over the top, and pair 4 off to the right. And why does this matter? Well, you grab a cable, you cut a cable in half, and you want to use this cable halfway through it, and you want to cut it. You can, but if one end is one way and one end is another way, you end up with hot pins and cold pins that are used completely differently. So if you take a look at all of these cables, one of the common things, and I'm glad we picked pin 2 as being high. It was great, because in a lot of audio installations, I'll get a lot of flack for saying this, but I usually use the colored pair as the hot, or as the positive of the signal, and I always use the white or the black or the the repeating color as the neutral color, or as the negative or the non-inverting. So if you look at these RJ45 connectors, it's 2, 4, 6, 8. Wouldn't that be great? 2, 4, 6, 8. Wouldn't that be great? But unfortunately, it's not. And what happened with a lot of different manufacturers is they started, doing different pinouts and different ways to go in terms of programmation, in terms of how they actually ordered things. So we had to make it very clear in the standard that there are 2 types of pinouts for these types of applications. And here we illustrated, I don't know who drew this, I think it was Richard Cabot, summarized it, I think, the most beautifully. When you put the 2 together like this, you see the blues always stay the same, and then the oranges move and the browns always stay the same. So I guess for me, I call it the ocean or the sky, and then the brown is the earth, and it never changes. But this orange and green, rotates back and forth between different pairs and different designations. So Ethernet polarity. So why does Ethernet work so well? Bill Whitlock told me, why does Ethernet work so well? Well, they have transformers on everything. True story, Ethernet. Every port you have, every switch you have, every device you have has a transformer on it. There is some type of receive transformer. There's some type of transmit transformer, every single one of them. And what they do is they use the pins between. So 1 and 2 and 3 and 6 as transmit. And then if you want to inject phantom power over top of it, well, what you do is you actually inject it into the center of a transformer and then receive it at the other end by tapping it out of the transformer for the conversion. But people say, well, okay, well, PoE, isn't this going to be dangerous if somebody plugs a microphone into a switch? Well, let me just tell you that PoE requires a negotiation to be activated. So unless your microphone has a PoE negotiation circuit built into it, there's no mechanism that will damage your switch, unless you have a PoE transmitter or PoE injector box that doesn't abide by the standard PoE operation. So Ethernet polarity. So does it have polarity? Well, yeah, of course it has a polarity. Well, it's a transformer, right? So it goes into a transformer, and there's a transmit and receive and a transmit and receive. But audio, again, Lester Bucks, the MBA, he needed to save some money, so he ditched all the transformers. So if you put all this together and you start looking at what these other manufacturers did in terms of, they didn't go 1, 2, 3, 4. These are the solid color wires. Some manufacturers, what they did was they actually took pair 1. They used pair 1 as the center. And then some of them used Ethernet. So if you look at the Ethernet, transmit is positive. So that's a J1. So J1 is positive on some of these, and the receive is negative on some of these. So 3 and 6. So 3 is positive, and some manufacturers went this direction where they used the positive and the negative, and what you ended up with is a mishmash of this solid pair order of, like, did it go 1 3 2 4 or 1 3 2 4 or 2 2 4 6 8? When I look at a cable or just grab an RJ45 cable, I look at it and I look at the solid color wires, and that's how I know if it's a TIA A or B. Again, I don't want to impose this, but I think of it as the sun, the sky, the grass, and the earth, and I look at that and I go, well, that's orange, blue, green, and brown, and I go sun, sky, grass, earth, and it's like, all right, there, it's a TIA B. I can't figure a nice, clever one for green, blue, yellow, brown. So if you have a clever one, it might be like, lily pad, lily pad, ocean, sand, dirt. Anyway, whatever you need to do to remember these things, when you plug all of these devices into different manufacturers' devices, none of these things work, or it's out of phase or something. In the case of AES3, phase and polarity do not play a part in these things. So it's more of just a channel orientation than anything. The polarity of AES3 in a balanced configuration does not affect the polarity of AES3 audio transmission. So, like I said, when you look at how they grouped pair 1, pair 3, pair 2, pair 4, pair 2, pair 3, it went all over the map. QTP4E, that's my pick of the choice, because it goes 1 2 3 4, 1 2 3 4, positive 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 positive, and away it goes. But we had to specify. And when you have this incompatibility in this industry, it's very important for us as purchasers and for us as users and consumers of this equipment that we ask the manufacturers to properly identify. So we surveyed, I don't know, maybe 50 manufacturers, and I'm not 15 to 20. There might be 20, 25 manufacturers doing this type of thing. And we came up with this chart that identifies the polarity of how they did it and why they did it. So the standard, defines that this is what a 4E is for everyone. That's it. The standard also goes in and talks about, what should the shield be doing? The quad twisted pair cable, it's like they're benefits from the twists, that's the magic, but shielded cat cable, it offers some different, but little in terms of magnetic interference rejection, right? Because it's again, I'm just gonna not talk about it. I'm gonna stop there, and that's really, it becomes a huge other discussion. I've already talked too much about it, but again, all of the practices, the one and only practices, where things need to be, applications where phantom power need to be, there has to be a return path for some of those cable shields. There's a lot of research to be done here. There's a lot of expertise that's already been done on projects like this to connect and interconnect stuff. Again, this is a new connector for us as an industry to pick and choose from. But going back to AES48, there's still a way that these devices should be built on the transmit end and on the receive end relative to the circuit. There's still a way that shield needs to bond to the shielding enclosure and reference that shielding point. Like, there's still huge design considerations that need to be paid attention to. So, you've got a ground. This is the ground of the chassis. There is that current flow that has to flow to that shield point to, the earth ground. And it's very important to realize that, if you have a device or a passive device, even, that this shield enclosure has to protect even the passive circuitry, right? Even the passive circuitry. There's equipment labeling in the standard. We talk about, well, okay, look, if you have a piece of equipment, we recommend a couple of things. Well, one, it should point connectors to the sky so the dirt doesn't fall. And then two, and your thumb is underneath, right? That's the norm. It shouldn't have lights on it. This is a great point. My friend from SMPTE actually gave me this point. He said, well, it shouldn't have lights on it. I'm like, okay, well, that's a good point. And it should say, well, this is the type that's on it. So it's AES72 4E. So very, very, detailed into the standard. It goes in to talk about a footprint layout. And I regret doing this, and I think there's a problem. We'll revise this because, like I said, it needs to have that shielding consideration played on it. But by breaking out those pairs, you can simply just do 1, 2, 3, 4, and away it goes. And a lot of those boards that I was showing above, and a lot of those circuits, there's a footprint. It's a A footprint. Nitric and amphenol make a footprint, but the A male and female can actually stack on top of one another. So if you were to make one of these little PCBs, you can put that A style footprint, and you can actually have the male and female on the same footprint and break it out into RJ45s. But in this case here, if you look, well, I don't really have a chassis. I really don't have anything to really deal with. So dealing with ground planes is something that us and the other groups are having the conversations about. Like I said, we talk about the orientation of the connectors. Dust and debris fall away from the electrical contacts. Like, this stuff is cheap. Again, back to Lester Bucks here. Like, it's super cheap. Again, the dimensions of all of this stuff is definitely delivered in other IEC standards. And I think in some of the working groups here, maybe in our next iteration, we'll remove some of the IEC standards and put, copies or redimensioning of those mentions in there, so it's a little bit more complete. And again, we talk about all the different category cable, that exist, and we just lump them under the QTP rating. If your folks are going to crimp, just a heads up. Solid crimps are different than shielded crimps or stranded crimps. So, solid is cheaper because it's just easy to extrude, right? You don't have to run it through a different process, thin it, bundle it. It's just a solid piece of copper, just gets a piece of plastic injected and molded over top of it and twisted, and that's pretty much it. So we recommend in the document that you should use standard for things that are fixed, and then things that need to move, like patch cables or microphone cables, we do recommend stranded. But again, as you get into the stranded, this stuff becomes microphonic, and as you move it around the stage. So the different shielding types make an impact. And again, it's a field for more study, and we can get a little bit more into it. And then, of course, there's tons and tons and tons of termination issues, right? But they're well known. And with this one tool that I can buy for $8, and every YouTube video trainer in the world, you can chop that off and have that whatever that seaside sound system was up and running. They're cheap, like I say. They're disposable. They're just absolutely a disposable technology that is starting to see adoption in all of these things. It becomes expensive to buy brand new XLRs every time you want to do a studio, or buy all brand new termination every time you do a studio. So thank you very much. I don't know how long I talked for. That's 40 minutes. That was 100 slides. It was almost 100 slides. So I'll talk a little bit about the pin 2, 16, 8, 5, 19, 8, 22, 11, 25 problem. And it kind of relates to this before I take any more questions or take any questions. The big problem with these DB25 connectors is a lot of them, that ground pin went directly to the signal circuitry or the signal reference. And what we're recommending and what has been discussed is this design technique of using a shield plane that bonds it to the chassis as soon as possible. So in some cases, it's not completely possible to have shield plane circuitry designed that way, but in the future designs, we hope engineers ultimately do something like that. Well, cheers. I guess what do we do now? We open it to questions, and that was a lot to digest. I'm sorry, folks.
Yeah, let's open it up for questions. Anyone have a question? I guess we put them in the chat window.
I have the chat window going here. We've got 43 people online. Congratulations, 43 people for sitting through a presentation like that. I appreciate it. Thank you. Yeah. It's very rare to have a stage like this to present on such a topic. How I got into this was this was a thesis project for college, and I've just maintained it from
here. Yeah, we will post a PDF copy of the slides on the website. Probably take a few days to get that up.
Yeah, I gotta blur some things and yeah. Well, I hope you go back on YouTube, watch it at half speed. Again, the standard it's not a huge read. Again, you think it's a simple concept, and that's really what I've learned from all of these standards is you think it's a simple concept, but ultimately, it turns into there are multiple different ways to
here's something
to do it. What do you got?
Here's something just popped up in the Q&A. Says, does the standard recommend shielded connections over unshielded?
You can do both. Like, the whole thing about it is you can do both. It depends on the transmitter and receiver, and that's the risky part. We recommend shielded connections when you're doing box to box. But again, all of the same problems that existed with shielded one end only operation, work. Those problems still happen. Do you think it's realistically feasible to make STP part of the standard, or is there so much UTP in the world it's difficult to ensure the shield connection through the system patch cords, et cetera, et cetera? Okay, so no, I think there's just such a ubiquity of UTP, unshielded twisted pair, in the world, and here, I'll put those on screen. So like, it's again, it comes down to system engineering. Like, the system engineering of this stuff can go a couple of different ways. Some people use the fourth pair just as the ground shield connection, and there were previous iterations of this type of connection that used like a pair of them as shield connections. But again, it comes down to the quality of transceiver. So, for example, like if you have patch cables that are built into the wall, well, one, you got to test it and trust it. You gotta make sure that it's doing what you think it's going to be doing. Some of the patch panels, when you recycle infrastructure, and this is the very interesting concept about this, using this QTP stuff in walls, is you can recycle infrastructure. Like there's just so much already pre-installed that you can actually move it. You can actually reuse it and recycle it. But again, if you were going to do a microphone preamp like how you would previously, like if you said you had a room that was in one place and you had some kind of system and patch bay, you would traditionally home run it. And really, when you make that shield connection for the microphone, and it's just such a low level signal, like there's no real, like it's just such a tiny voltage that you really want to do everything you can to actually protect it. So driving signals with microphone preamps across this is a better thing. For me, I am not one who recommends using this as a microphone snake over UTP. I'm one to say, if you want to use a microphone, you have to use an STP cable for your shield. But then you also have to follow the other rules, which are, well, it has to be bonded to the shield enclosure in the proper ways. And again, we're not there yet to say this is the way to do it, because we don't have that much data on it yet. But there's so many systems and patch bays throughout the world. Like it's impossible to ensure that shield connection is there throughout the whole thing. Again, some of these things, it's a common return path to ground. Phantom power and microphones. These are problems that plague us. But when it comes to the world of AES3, and when it comes to the world of analog line level differentially driven audio, they do not succumb to the same type of problems that something like a microphone or a transducer would. I'm sorry, Phil, that was like a 5-minute answer to a 3-line question. I'm sorry. I answered that live. Cheers. Some of the things, I've been told, this is not a new concept. The broadcast industry has been doing this for a long time. This is putting things on tieback trees is not something that they teach in recording schools, right? Putting twisted pairs and the benefits, it's not something it's not low level. It's not as low level as it once was. So with some kind of standard to interconnect these things, there's an opportunity for device manufacturers and users to really simplify their systems. Like I said, for me, it's mobiles, moving things around, putting, those, big, huge 8-channel snakes, from one piece of equipment to another piece of equipment is cost prohibitive to some people. A lot of audio equipment ends up in the trash or in the garbage because it's just so costly to interconnect the wires between console and recording equipment. So, the barrier to entry for audio engineers, this reduces that barrier to entry if you use the technology cleverly. I'm starting to see broadcasters, broadcast makers of broadcast equipment, shift from 2-channel. What they used to do is a 2-channel plus a shield with some power. But they're starting to shift over to AES72, and we're starting to see more and more of that. It was, before it was very expensive, very bespoke multi-pin connectors. Before the DB25, there was Elcos and EDAX, another Canadian company. They ultimately distilled it down to the most available thing, which is the AES59 DB25 connector. And then this is even distilling it down even further to the more ubiquitous 8P, 8C Ethernet connector that is already predetermined. But our biggest challenge is I want to recycle this, this pre-made patch cable. I can't make it this good. No amount of soldering and crimping will be able to make this molded plastic cable as good as whoever made this. All right, that's all I can do. I got 50 minutes. That was a lot. Thank you, everyone. Christopher in the comments says, thanks. Lots to think about. Yeah, there is a lot to think about. There's and I recommend if somebody's in the schools, take a look. Do some experiments. Go right now. Everybody, just go to that 5-foot cable. Just take it wherever you are right now. Just go. Cut it in half, open it up, let's just strip it back. Here, I'm going to strip this back. Okay, we're going to strip it back. Everybody just go, take the afternoon off, go and, blazing through that much information. Yeah, I did go through that much information. I'm sorry. It's coffee. I'm a coffee addict. I don't know if anybody else is a coffee addict here in the Audio Engineering Society, but yeah, it's kind of like my lifeblood. Of course, I don't have the right strippers. Anyway, I'm going to use my teeth, at an AES presentation to strip some wire. Yeah, right. Hold on. Let's see if I can get this thing open. But again, take the afternoon. Thank you,
Right.
Phil. Thanks for coming. Thank you, Rich.
Thank you, everybody, for attending. And,
Go open up some cat cable.
let Anthony get back to stripping cables and drinking coffee.
Yeah. Drink some coffee. Go solder some XLR cables. Prove me wrong. I appreciate it. You know, I want everybody to prove me wrong. Please come to the SC meetings, the subcommittee meetings, to prove us wrong, to prove us right. We also look for people to prove us right too. So thank you, Uno. Thank you, Eva. Everyone, have a great day.
I will note that we have the fall standards meetings coming up in a few weeks, and you can find a complete schedule on the AES website under AES standards. Look at the standards tab and you'll find the meetings listed, and I encourage all of you to attend. Thanks again for attending this.